the YouTube platform is still in internet lockdown. That's why I've not been able to upload lectures for the previous lecture. That's why I've not been able to upload videos and give you the links. But hopefully, when the system is restored, I'll be able to upload and update you accordingly. Okay, so we've been looking at the inner product spaces. That is chapter 3, and the applications of the inner product spaces. Last time we looked at how we can compute the norm of a vector. We defined what it means by a vector in an inner product space being orthogonal and being orthonormal for that matter. So now today we want to look at how we can construct orthogonal bases. Bases is the plural form for basis. So if we have, for us to have an inner product space, we must be having a vector space V. And that vector space V, one of the properties is that it should be having a basis. So in today's lecture, we want to look at it. We want to look at how we can make an arbitrary basis for the inner product space V into an orthonormal basis. First of all, we need to make it an orthogonal basis. And once we make it an orthogonal basis, there's a theorem that we are going to look at. And that theorem tells us that every orthogonal basis can be normalized to give us what we call an orthonormal basis. So this is our plan for today. We'll talk about orthogonal bases. We'll talk about the coordinate relative to orthonormal bases. Talk about the orthogonal projections, and then we'll talk about the Gram-Summit orthogonalization process. So we start with a definition. If we have a set of vectors v1, v2 up to vn in an inner product space, then that set is said to be orthogonal if each pair of distinct vectors in S is orthogonal. So that means if for any vi, vj, the inner product of vi, vj is equal to 0 for all I different from j. So this is what we mean by two vectors being orthogonal. In the previous lecture, we defined what it means by two vectors being orthogonal. Now, here we want to define what it means by a set of vectors being orthogonal. So, in the previous lecture, we said two vectors v1 and v2 are said to be orthogonal if the inner product of v1, v2 is equal to 0. Now, for a set to be orthogonal, each pair of distinct vectors should be orthogonal. Distinct vectors, we mean we don't require that v1 is orthogonal to itself, but we require that v1, v2, v1, v3, v1, and so on up to vn. Then v2, v3, and so on. Remember, inner product of v1, v2 is the same as the inner product of v2, v1. So we require that each pair of distinct vectors is the orthogonal. If that is achieved, then we get an orthogonal set. Then lastly, we want to define what it means by an orthonormal set. Again, we defined what it means for a vector to be orthonormal. A vector is said to be orthonormal if it has. Who can tell us what it means by a vector to be orthonormal? Who can remind us what we talked about a vector being orthonormal? Hello, do I have people here? Katongore, what did we say about an orthonormal vector? Members, are we still together?
Yes.
Anyone who remembers what we talked about an orthonormal vector? Katongole James.
Yes, sir.
What did we talk about an orthonormal vector? Forgotten? Hmm? Okay. Okay, it means people did not take
Yes.
time to read. They were busy working on assignments, but we said a vector is said to be orthonormal if it has norm 1. The definition is even on your screen. An orthonormal set, an orthogonal set in which each vector has norm 1 is orthonormal. So that means a vector is said to be orthonormal if it has norm 1. Are we together?
What do you mean by saying if it has a norm 1?
Yeah, we looked at how it means that when we compute its norm, the answer should be 1. Just like a unit vector. Do you know what a unit vector is?
Yes.
So it means when you get, like when you take the magnitude of a unit vector, it gives you 1. Likewise, when you take the norm, using
1.
the other definition of norm that we looked at, then when you take the norm of that vector, the answer should be 1. If that happens, then it means that set is it. And I mean that vector is
Orthonormal.
an orthonormal. We say it is
Orthonormal.
orthonormal vector, okay? Then a set whose all
Yes.
vectors are orthonormal is called an orthonormal set. Are we together?
Yes.
Okay. Next, we can have a look at a simple example of a set which is orthogonal and a set which is orthonormal. So one, we have a set, we have vectors u1, u2, and u3. B vectors in R3. Assume that R3 has the Euclidean inner product. We say the Euclidean inner product is the usual dot product. Then you can see that the inner product of U1, U2 is equal to the inner product of U2, U3 is equal to the inner product of U2, okay, U1, U2, U1, U3, U2, U3, and it is equal to 0. That means each pair of distinct vectors is orthogonal, and so it means a set S which has vectors U1, U2, U3 is an orthogonal set. How do we know that the inner product of U1, U2 is 0? We take a dot product of U1 and U2. Of course, it is 0 times 1, which is 0, plus 1 times 0, which is 0, plus 0 times. So it gives us 0. Inner product of U2, U3. It is this gives us 1. This gives us 0, and this gives us 1, I think.
0.
No, this is
So
1,
1.
and even the first one is 1. Okay, there's an error here. You see, this U2 is the same as U3. So this was supposed to be a different, it was supposed to be a different vector. Okay, this one had a negative. U3 has a negative here. For it to be orthonormal, this one should be having a negative. We can take note of that, such that this one becomes 1, then plus 0, then minus 1. So you get 0. So if a set has each distinct pair being equal to 0, then it is said to be an orthogonal set. However, when you look at the norm of U1, it is 1. How do we get the norm of U1? We looked at how we take the square root of the inner product of U1. So when we normalize, we get this squared plus this squared plus this squared under root. So norm of U1, it is 1. Norm of U2, it is root 2. The norm of U3 is root 2. That means that it is not an orthonormal set. So here we have looked at an example of a set which is orthogonal but not
Excuse
orthonormal.
me, sir.
Yes,
How do we get to know that the norm of U1 is equal to 1?
we compute the norm of U1 by computing the norm of U1. How do we compute the norm of U1? In the previous lecture, we said we take the square. We define the norm actually as the square root of the inner product of U1 U1. Remember, we are talking about the Euclidean inner product.
Mm,
I don't know if it is clear.
yes.
Yeah, so yeah, using that formula, the square root of inner product of U1 U1. Now, inner product of U1 U1 with the Euclidean inner product space is dotting this vector with itself, and when we do it, we get 1. Okay.
Yes.
Then for U2, inner
Yes.
product of this, it is going to be 1 plus 1, which gives us 2, but then square root, we get root 2.
Mm,
Yeah. So a set can be orthogonal when it is not orthonormal. Okay, next we look at an example. Another example, we have vector space V, which is R2, with the Euclidean or standard inner product space. The standard basis for R2, it is 1, 0, 0, 1. Basis means that every element of R2 can be written as a linear combination of these two basis elements. So this set is an orthonormal set. First of all, a set cannot be orthonormal unless it is orthogonal. But a set can be orthogonal when it is not orthonormal. So we can see that this basis B2 also, with this set B2 also, which is 1 over root 2, 1, 1, 1 over root 2, it is also an orthonormal set. We can check. How do we check? We check that the norm of this vector is 1, norm of this vector is 1. So it means it's orthonormal. Likewise, here we check the norm is 1 norm. So here we have an example of a basis which is orthonormal. Okay, now we can talk about the orthogonal basis. We can talk about the orthogonal basis. How do we make?
Excuse me,
Yes, please.
I'm requesting you to go back to the previous example, that second last requesting for explanation there on B1 and the basis of B2.
Okay, B1 is just any set. Let's first look at it as a set before it becomes a basis.
Yes,
So we are saying
yes.
that B1, this set B1 is orthonormal. And
yes.
why are we
After
saying it is
checking,
orthonormal? Because each vector in that
Because
set,
it has 1. It has a norm.
has norm 1.
okay,
And how do we know it has norm 1? We are talking of the standard basis, which is the inner product of this element with itself, and then its norm is computed using the other method I explained, which is even in the notes, which we even talked about in the previous lecture. So we compute the norm here, it is
yes,
1. Even when we compute the norm here, it is 1. So since each vector in B1 is orthonormal, then it means B1 is an orthonormal set.
Mm.
Same story with
Then
B2.
okay.
Irene, are you okay?
Now part B.
Mm.
B2.
Mm.
I'm not seeing the one in the set.
You're not seeing one.
Mm.
You're not seeing how it is going to be or how each vector is
It
orthonormal.
is going to be one.
It is going to be when you take the norm.
I'm saying
Hey,
now here when we take the norm, I'm not getting the one.
what do you get?
Zero.
Mm-mm. For the second element, are you talking about the second element?
Yes.
Now, the second element, you take when you take the dot product of this element with itself, the negative times the negative will give you positive. Actually, we can look at this as 1 over root 2, 1 over root 2. So when you're dotting it with itself, it is 1 over root 2 times 1 over root 2. That one gives you a half. Plus negative 1 over root
Yeah.
2 times negative 1 over root 2. That one gives you a half.
Half.
Because it's negative times negative. So a half plus a half, you get 1.
Yes. I've seen it.
Your problem was negative times negative. Okay.
So now, sir,
Yes.
we to conclude that it is orthonormal. That means it should be the norm should be 1
For each vector in that set.
for each vector. That
Yes.
means if I dot, for example, if I call that the first one of B1, if I call the first vector 1, 0, if I call it U1,
Mm-hmm.
and I call the second one U2.
Mm-hmm.
So if I get the dot product of those vectors,
Mm.
U1 and U2,
Mm.
uh, I get 1.
Uh-uh.
And if I get their
No.
norm, it is
Let me
also
let me
1.
help you. Let me help you. When we are checking orthonormal,
Yes,
when we talk of a vector
yes,
being orthonormal, we are talking about one vector. Okay? When we talk of
one vector.
orthonormality, we are talking
Yes.
about one vector. So we check one vector after the other. So we check if U1
Oh,
is orthonormal. How do we know U1 is orthonormal? We compute the norm of U1. If the norm of U1 is 1,
okay.
then it is orthonormal. Compute the norm of U2. If the norm of U2 is 1, then that means U2 is also orthonormal. So if all vectors in a set
Mm,
are orthonormal, then it is an orthonormal set.
okay.
Yeah, then for when we
Okay.
talk of orthonormal, we are looking at an individual vector. When we talk of orthogonal, then two vectors. That's when we compute the
We are
dot
looking for
product
two
of the
vectors.
vectors. But bearing in mind that we do dot product if the inner product
Mm,
is the Euclidean or the standard one.
okay. What do you mean by standard one?
Standard is it is the usual. The standard is the usual, the known one. Like the obvious one. Of course, we can, like for this R2, we can get other, actually even this one is a basis. B2 is also a basis for R2. But the
Mm,
quickest one we can think of, or the standard one, is this B1. So it means
okay.
R2 can have more than one basis, but there is the standard where we base from. You see, we build from this to get B2.
Mm,
Yeah.
okay.
Okay, so we now talk about the orthogonal basis. We let V be a non-zero vector in an inner product space V. Then, so here we are discussing how we can make an arbitrary basis orthogonal, because we can have a basis which is not orthogonal, like we saw in example 1. But here, we know that if we have any V is any vector in the vector space V, then this one here is a unit vector. To get a unit vector, we get the vector, we divide by its norm, or we can look at the norm as the magnitude. We looked at how to get unit vectors when we studied um, vectors in senior 3. So this is when we get a vector V divided by its norm, then the resultant is a unit vector. V hat is a unit vector, meaning that V hat will have norm 1. Since when we take the norm of taking the norm of V hat is the same as taking the norm of this, and when we take the norm of this, if it is raining in the whole village, then it is raining on individual house. So here we get this divide by that and we get 1. So that means we can make any vector orthonormal by dividing it by its norm. And thus, an orthogonal set of non-zero vectors can always be converted into orthonormal set by normalizing each vectors. So that means once we have an orthogonal set, then we can change it into an orthonormal set. What do? We normalize each vector. How do we normalize each vector? We get each vector divided by its norm. Are we together? People, are we together? Talk to me, talk to me.
Yes.
Yes, sir, we are together.
Okay, so
We are together.
what we have talked about here is that if you have any vector, then when you divide it by its norm, it changes into orthonormal. So that means we can change an orthogonal set into an orthonormal set by normalizing each vector. Okay. I have 10 minutes to the first break. So when I'm switched off, we take like 2 minutes. Look for the code from WhatsApp and log in. Okay, so next we look at the theorem. This theorem is going to tell us how we can get a coordinate relative to an orthonormal basis. In chapter 2, we looked at how we can get coordinate vectors relative to bases, to the basis and the change of basis. We looked at that in chapter 2, but now that we are talking about orthonormal basis, then we want to look at the coordinate relative to that. Now, this theorem is telling us that if we have an orthonormal basis for an inner product space V, and U is any vector in V, then that U can be written as this linear combination. It is U, inner product of U V1 times V1, plus inner product of U2 V2 times V2, plus and so on up to inner product of U Vn times Vn. So this theorem is telling us that if we have an orthonormal basis for an inner product
Open.
space, yes. Any problem, Irene?
No.
Okay.
No.
Okay, so we want to prove this theorem. Since this is a basis for V, then it means that any vector U in V can be uniquely expressed as a linear combination. It can uniquely be expressed as a linear combination of these basis elements. So that's what we know. And then it remains to show that actually the constant K1 is U V1, K2 is U V2, and so on up to Kn is U Vn, because we want to check that U is this linear combination. And you see, it is, if this is a basis, then U can be written as a linear combination. So we want to show that K1, it remains show that K1 is inner product U V1 and so on. So, but we know that the inner product of U Vi, okay, V1, we can start with VI. Okay, VI. From the properties, I think that was the I3 of the inner product space. The inner product of UVI is the same as inner product. We can write it as the inner product because we know that U, from what we saw previously, since U is a vector, it can be written as a linear combination of basis elements, then VI. And we know since K is a constant, again, products of inner product space, we can put a K constant out, so it will be K inner product of V1, VI plus K inner product of V2, VI, and so on up to Kn. So we get there. And since this is an orthonormal set, it means, since it is an orthonormal set, it means that it is orthogonal. Every orthonormal set is orthogonal. So it means that all these inner products are going to be zero for I different from J, and we pick only one. We pick only one. And if they are the same, then we get this one, which is the same as the square of the norm, which gives us 1, which gives us 1. So it means that the inner product of this is equal to K, VI, and so on and so forth. So that one will always generate KI, meaning that when you take inner product of V1 and V1, if we take V1, if we take I equal to 1, then all these will be 0 apart from V1, V1. But V1, V1 is the norm of V1, which will give us 1 since we are talking of an orthonormal basis. So here we get K1, here we get K2, and so on, we get Ki. Thus, the inner product of this is for each I. It follows that this is an orthonormal basis for U, and U in V can be written as U with relative, okay, U relative to the orthonormal basis S. So we get the inner U1, V1, inner U, V2, and so on up to the inner product of U, Vn. So this one gives us the coordinate of U relative to this orthonormal basis S. Let's have a look at an example. We have 3 vectors V1, V2, V3. We want to express U1, we want to express vector U as a linear combination of the vectors in S, and then we find the coordinate vector V relative to S. First of all, is a set of vectors V1, V2, V3 orthonormal? Is it an orthonormal set? Members, what do you think?
I don't know the question.
Is this set comprising of vectors V1, V2, V3, the way you're seeing them, is it an orthonormal set? In other words, are all these vectors V1, V2, V3 orthonormal?
Yes.
Eh?
That's not I.
Mhm.
Maureen,
Autonomous.
Is it?
It is.
It is. Others, what do you say? Eileen, are all these vectors orthonormal? Eh? Are all these vectors orthonormal? Okay, so from when we look at them, they are all going to be orthonormal, and that's what we can always check. So we want to write U as a linear combination of the V1, V2, V3. And so it is easy to check. The checking is an exercise that a set which has V1, V2, V3 is an orthonormal basis for R3 with the Euclidean inner product space. So, since it is an orthonormal basis, it means that this U from the theorem we saw can be written as this linear combination. Can be written as this linear combination. So inner product of U V1, it is going to be 1 because we are talking over, okay, it is, we can compute it. This one can be computed. So we compute inner product of U V1. How do we get that? If U is this, so is V1. So we are taking the dot product of U V1. It is going to be 1 times 0, which is 0, 1 times 1, 1, 1 times 0, which is 0, so we get 1. The inner product of UV1 is 1. Inner product of UV2, it is minus 4 over 5 plus 0 plus
1 over
3
5.
over 5, so it gives us 1 over 5. Inner product of UV3 is 3 over 5 plus 0 plus 4 over 5. That one gives us 7 over 5.
7 over
So the inner product of this is that, inner product of that is minus 1 over 5, inner product here is 7 over 5. So that means this is the linear combination is 1 V1. Then negative 1 over 5 V2 plus 5 over 7. So the coordinate vector U relative to the orthonormal basis S, it is 1, then 1 over 5, then 7 over 5. So this is the coordinate vector that we are talking about.
So,
Okay, so we can take a break and then when we come back, we talk about, we continue to look at the orthogonalization process. We are now done with coordinate vector relative to that. So we are taking a break.